Hey guys, now we're going to talk about inertia and Newton's first law. So first, to define what a force is. On the previous set of notes we talked about the types of forces that are present, but you need to know that every single force is a push or a pull that an object experiences. Whether it's one that the object is touching, whether it is one that it is felt through a field force, as long as it is a push or a pull that an object experiences, it counts. Forces can cause an object to accelerate. They don't have to accelerate, but a force has to be present for acceleration to be taking place. An object moving at a constant rate may have a force acting on it, but it may not. Why not? If it is moving at a constant rate, velocity is constant. And if velocity is constant, acceleration is 0 meters per second squared. So there could be a force present, or there could not be a force present. So there are two scenarios. The first scenario is that there is no force present, but is a frictionless surface. The second scenario is that there is a force present, but friction is the same amount. So it's equal to that force. In these two scenarios, the object will not accelerate, which means that the force is not overcoming the friction. So in both of these scenarios, even if a force is or is not present, there will be no acceleration. So either A, there is no force present and it is a frictionless surface, which means that the object will be moving with a constant velocity and not speeding up or slowing down, or B, the force is present, but it's equal and opposite that to the frictional force. So we have to understand the idea of net force, and net is just a fancy math way of saying total force. So net force is defined as the sum of the forces acting on an object. The two objects that we have acting to the right have two different amounts of total force. Okay, the top one, we have 10 newtons going to the right, and we have 5 newtons going to the right. This net force has a value of 15 newtons. In the bottom picture, we have 10 newtons going to the right, but 5 newtons going to the left. So that means that these forces do not act together, they actually act against each other. And our total net force is 5 newtons to the right. These two examples are considered unbalanced forces. This means that the force acting on the object is equal to any number that is not 0. If the net force is any number other than 0, that means the object will accelerate. In these examples, we have the net force acting on the objects to the left. On the top one, we have a net force of 0 newtons. So this is like a tie in tug of war. 5 newtons pulling to the left and 5 newtons pulling to the right. This is considered a balanced force. That means that the total force on the object is 0. So these other two diagrams, can we make them balanced? This one, we have a sum of 10 newtons going to the left, so we can add a single arrow going to the right that has a value of 10 newtons. Here we have 3 newtons to the left and 10 newtons to the right. So in order to have these equal, we need to add more to this side. The difference between 3 and 10 is 7. So I'm going to draw another arrow and I'm going to write 7 newtons above it. So these are balanced, which means the net force is 0, which means that it will not accelerate. When the forces acting on objects are 0 or add up to 0, two things are possible, and we've already kind of mentioned this. The object is either moving, but there is no frictional force acting against the motion, which means it's not accelerating and moving at a constant velocity. There is no force acting on an object, but there is no friction either, and the force is moving at a constant velocity. Or the object is sitting still and not moving at all. So the difference between the top two. In the first one, we have a frictional force, which happens to be equal and opposite to the force applied. The second one, we do not have a frictional force, so it's moving at a constant velocity anyway. So inertia, Newton's first law. Newton's first law states an object will resist change in motion. We more know this idea as the phrase, an object at rest stays at rest and an object in motion remains in motion unless acted on by an outside force. Most of the time people forget to add that extra little snippet, unless acted on by an outside force. So if you have a system where an object is sitting at rest, you have to apply an additional force to make it move. Or if you are in space and someone throws a wrench in one direction, their body will move in the opposite direction. They will do that until they run into something because there is no friction slowing it down. The larger the mass, the larger the resistance to change. I like to use the example of a semi-truck getting on the highway to explain this last bullet point. If you've ever driven or been in a car behind a semi-truck, it's not necessarily a fun thing to be stuck behind them as they try to accelerate on the highway. They have a larger mass, so they tend to take a lot larger amount of time to get up to traveling speed. It's the same in the other direction. Semi-trucks and trains take a lot of time to slow down because once they are at traveling speed, they don't actually want to change. So if you've ever seen a train accident where a train gets derailed, it may hop the tracks a half a mile or a mile down the road, but still continues to move because it has that inertia built up from its motion already being there. So we have a couple examples of inertia. The first one is tripping and falling forwards. If you've ever been walking down the road or walking down the hallway and you've kind of scuffed your foot on the ground, your body will continue traveling forward because that's the direction you were originally moving. Okay, you don't necessarily trip and fall backwards unless somebody pushes you over. So when you trip by yourself, because you're clumsy, like me, you fall forwards because that's the direction you were moving initially. Another example is a bed of nails. At circus shows, they tend to have somebody lay on a bed of nails and put a cinder block on their chests, and someone breaks the cinder block with a hammer. Well, when they stand up, they actually don't have any spots on their back that are bleeding. They might have little indentations of the nails, but it never actually punctures any skin. The reason that they do this is because the cinder block has such a large mass that it has a high inertia and it doesn't really want to move. So when someone hits it with a sledgehammer, it moves just a little bit, but not enough to actually push the person into the bed of nails. Another example is turning in a car. If you've ever been in the middle back seat on a car trip, as you turn around corners, you notice that you always shift to the outside of the car. So if you're turning right, your body shifts to the left. If you're turning left, your body shifts to the right. That's because your body wants to continue moving forwards, and when the car moves, your body has to adjust to that change in motion. So when there aren't really math examples for Newton's first law and the idea of inertia and not wanting to change your motion, we are going to practice with balanced and unbalanced forces using free body diagrams. Alright, I'll see you guys soon.